Hello. In today's lesson, we're going to look at the sum and difference identities in trigonometry. You'll see on the screen these 7 guided questions that will make up this lesson. We'll start by talking about what the sum and difference identities are, and then how we can use a sum or difference identity to calculate an exact value for a ratio like the sine of 11 pi over 12. And once we've discussed what the sum and difference identities are and how to use them, then we're going to talk about proving some of them. So why is it that these identities work and why is it that they exist? And we'll look at that in questions 3, 4, and 5. And then finally, for questions 6 and 7, we'll look and see, is there such a thing as a sum or difference identity for tangent? And if so, how can we use that? Okay, so let's get to it. So what do we mean when we talk about the sum and difference identities in trigonometry? Well, we basically mean these 4 formulas here. 2 of them are sum identities. The first one, the cosine of A plus B, and the third one, the sine of A plus B. And 2 of them are difference identities, the cosine of A minus B and the sine of A minus B. They basically provide you a way to calculate the cosine or the sine of either a difference or a sum of 2 angles using those 2 specific angles, A and B. If we look at our next question, we will see how we can use, in this case, we're going to end up using the sine addition formula to come up with an exact value for the sine of 11 pi over 12. How do we do that? Well, we need to realize that although we don't know the exact value for an angle such as the sine of 11 pi over 12, there are many angles that we do know the exact value for. Those angles are summarized in our special triangles. So we're able to figure out either sine, cosine, or tan for pi over 4 or 45 degrees, or pi over 6, which is of course 30 degrees, or pi over 3, which is 60 degrees. So what we're going to do is we're going to use the ratios that we know to figure out what the sine of 11 pi over 12 is. Now, obviously, 11 pi over 12 is not one of the angles we have in those triangles, but I can break 11 pi over 12 up just like this. 11 pi over 12 could be written as 8 pi over 12 plus 3 pi over 12. And I like that because 8 pi over 12 reduces to 2 pi over 3. And 3 pi over 12 reduces to pi over 4. And I can use those values because my special triangles, I mean pi over 4 is right there in one of the special triangles, but they also provide me with ways to calculate exact values for any angle that's either in quarters, thirds, or sixes, and 2 pi over 3 is in thirds, so I can do that. So calculating the value of sine 11 pi over 12 is really the same as calculating the value of sine pi over 4 plus 2 pi over 3. Of course, to do that, I'm going to want to use the addition identity for sine. And there it is. Here my A value is pi over 4 and my B value is 2 pi over 3. So let's use that formula to sort of, you can think of it kind of expanding this expression right here. We will get the sine of pi over 4 times the cosine of 2 pi over 3 plus the cosine of pi over 4 times the sine of 2 pi over 3. Now, as I go to evaluate these 4 trig ratios, notice the sine of pi over 4 and the cosine of pi over 4 are the easiest ones. They're right here in this triangle. They're both 1 over root 2. So I can fill those in right away. 1 over root 2, 1 over root 2. Now, I also need to calculate the value of the sine of 2 pi over 3 and the cosine of 2 pi over 3. Now, that's going to be a little bit more work because those are not acute angles. So we need to consider what those would look like on either the unit circle or just on the Cartesian plane. So let's do that now. So keeping in mind that 180 degrees or pi radians, I'm at 2 pi over 3. So I'm 2/3 of the way of a half rotation or 180 degrees. So the angle 2 pi over 3 is going to land somewhere over here, okay, where this is now 2 pi over 3. And your pi over 3 are 1/3 short of a full rotation. That is one of our special triangles. So the hypotenuse is still 2. Okay, this side here would be not 1, but -1 because we're now on the Cartesian plane. And of course, √3. And that tells us that the cosine of 2 pi over 3 is in fact equal to -1/2, whereas the sine of 2 pi over 3 will be equal to √3 divided by 2. And so we can use those values. So now we put -1/2 in for 2 pi over 3 and √3 over 2 for the sine of 2 pi over 3. Now we want to figure out what we get next. Well, -1 times -1 gives us -1 over 2√2. And 1 times there should be a plus here, plus √3 over 2√2. Putting those together gives us -1 plus √3, all divided by 2√2. Now, that's fine for a final answer. We generally, in math, try to avoid irrational numbers and denominators of fractions. And in this case, √2 is the irrational number. So we can rationalize that expression by multiplying by √2 over √2. And when we do that, we get -√2 plus √6, all divided by, so the √2 times √2 just gives you 2 multiplied by 2 to give you 4 as a final answer. Or if you want, it looks a little nicer sometimes if you write √6 minus √2, all divided by 4. The next part of the lesson, we're going to look at why these trig identities, sum and difference identities, exist, why they're true. So far, they're just formulas that have been given to you, and now we'll look at actually proving them. Now, it might seem kind of strange, but we're going to start with the difference identity for cosine, because as it turns out, it's the easiest one to prove to start. Now, having said that, this is not an easy proof. This is meant to be a guided proof. This is not something you probably come up with on your own. So bear with me. I think it's worth looking at this anyways, even though it's hard. We're going to do something a little different here. We're going to take these two angles A and B, and we're going to assume that they're angles that have been drawn on the unit circle. Every angle can be drawn on the unit circle, and that's what we're going to do here. So now you can see I have my unit circle here. Let's just zoom in a little bit and make it a bit bigger. Now, I really don't know anything about angles A and B, but I do know I can draw them on the unit circle. I'm going to assume that angle A is obtuse, and that when it's drawn, it ends up rotating from the positive x-axis, and it ends up over here somewhere. Okay, so we're going to call that angle A, and I'll just label it as angle A. Okay. Angle B is also an angle, and I'm going to assume it's quite a bit smaller. Let's say that angle B only rotates this far. It looks like it could be like 30 degrees or 20 degrees or something. It doesn't really matter though. So that's angle B. Okay. Now, two things, very important things about these angles. Since this is a unit circle, the radius of the circle is 1. This has a length of 1, and so does this right here. Now, remember that points on the unit circle give you the cosine and the sine of the angle they correspond to. So for example, at angle B, it will always land on the cosine of B and the sine of B for its x and y coordinates. And then in a similar sense, angle A, we have the cosine of A and the sine of A for the point that it lands on right here. Another thing to notice is although this is angle B and this here is angle A, that means if you took angle A and you subtracted angle B, that's this angle right here that separates those two sides that have a length of 1. They're called radii. So we can label that in our diagram here. This is A, take away B. Okay? Okay. Now, the gist of this proof lies in the fact that there are actually two ways to calculate the distance between these 2 points right here. So I'm going to draw a line across here, okay? And we're going to call this distance, I'm going to call it D, D for distance. And notice the triangle we have here. From here to here. This triangle has a side length of 1, another side length of 1, and an angle of A minus B. So we're actually going to come up with an expression for D. We're actually going to end up finding D two different ways. And the first way I'm going to find it is using the cosine law. So the cosine law tells me that D squared is equal to 1 squared plus 1 squared, subtract 2 times the cosine of A minus B. Okay, that's that cosine law. C squared equals A squared plus B squared minus 2AB times the cosine of C, where here our A and B sides are both 1, okay, and our angle is the angle A minus B in this green triangle here. I can clean that up a little bit, and I can say that D squared must be equal to 2 subtract 2 times the cosine of A minus B. Now, as it turns out, that, using the cosine law, is not the only way to calculate the distance between these 2 points. So what we're going to do is we're going to give another method to do the exact same thing. So we're going to find this. So we're going to find that value D again, but this time we're going to use a different formula. We're going to use the distance between 2 points, or the length of a line segment formula. So when you're working with analytical algebra, if you remember learning about the distance between 2 points on the Cartesian plane, there's a formula for that. So here's that formula I'm talking about. The distance between a point x1, y1 and a point x2, y2 on the Cartesian plane is given by this formula right here. And it's just because of Pythagorean theorem. Okay, a line segment here is the hypotenuse of a right angle triangle created by the rise and the run. And of course, the rise is y2 minus y1, and the run is x2 minus x1. So D squared would be equal to this squared plus this squared, or D is the square root of that. I'm actually going to write this formula as D squared is equal to x2 minus x1 squared plus y2 minus y1 squared, because in my example, that's what I'm going to use. So if I go back up here, I want to find D, but this time my points, my x1, y1 point is going to be this point right here, and my x2, y2 will be this point right here. So filling them in, this is what I get, okay? So x2 minus x1 was cos B subtract cos A squared, and my y2, y1 is sine B minus sine A squared. And the next step is to realize that I have calculated D squared two different ways. One using this formula down here, and I get this expression right here, and another using the cosine law, and I get this expression right here. I'm actually going to call this equation 1, and I'll call the second one equation 2. If D squared equals this and D squared equals this, then it must be that these two things are equal to each other. So we're going to combine equations 1 and 2, and we'll write that next. So when I combine 1 and 2, I will get that 2 subtract 2 times the cosine of A minus B is equal to cosB minus cosA squared plus sine B minus sine A squared. Just like that. Okay, well, where do I go with this? Well, you might notice, if you actually remember what it is we're trying to prove, that we're trying to find the expression for the cosine of A minus B. And so there's some rearranging that we're going to do now, and it's just algebra that's going to help us solve for the cosine of A minus B. So the first thing we're going to do, we're going to take this right side, and we're going to expand it. And it's going to get a little bit long. Well, let's see what we get here. And there you have it. Now all I've done here is taken cos B minus cos A squared, and I've used FOIL to expand it. So I get cos B times cos B gives me cos squared B. I get a negative cos A cos B for my outside term, and then my inside term using FOIL is also cos A cos B, so I get -2 of those. And then, of course, let me fix that, sorry. Cosine of A times cosine of A gives me cos squared A. So those first three terms come from this expansion, and the last three terms come from this expansion right here. You'll see the last one, sine A times sine A, I actually had to put on the next. I couldn't even fit it on the screen here. So that's what I get when I expand that. Now, remember Pythagorean identity, that sine squared A plus cos squared A equals 1. And I can see I've got a sine squared A here and a cos squared A here. So that's going to equal 1. Sine squared B plus cos squared B will also equal 1. So really, what do I have left? I get a 1 plus a 1, which is 2. Subtract 2 cos A cos B minus 2 sine A sine B. Okay. Next, I can divide everything by 2. You'll notice that every single one of those terms is a multiple of 2. So let's do that next. And there you can see that. Now, keeping in mind, I'm trying to come up with the equation for the cosine of A minus B. So I want to solve for that. Now, notice that if I were to then do that, notice that the 1's here actually just cancel off on each side. And then it's just a matter of multiplying both sides by -1. And I get cosine of A minus B is equal to the cosine of A times the cosine of B plus the sine of A and the sine of B, which is exactly the identity I wanted to prove. So not a simple proof, the most difficult proof we will ever look at in this course even, and there it is. As a quick review, what did we do here? Well, if we go all the way back, we started off by drawing A and B on the unit circle, which gave us these 2 points, and then we calculated the distance between those 2 points 2 different ways. One way was using cosine law in the green here. The next way, was using the distance between 2 points on the Cartesian plane, which gave us this formula right here. We combined both those formulas, and then the algebra took over. Moving on to question 4. How about we prove the addition identity for cosine? Now, if you made it through the subtraction identity, you're probably thinking, I can't handle another one of these. But relax, now that we have proved the cosine of A minus B, this formula is actually pretty easy to do. Let me show you. I can use the formula that we just proved, the difference identity for cosine. So what we can do is we can realize that the cosine of A plus B is really the same as the cosine of A take away negative B. So adding could be thought of as just subtracting the negative. So then we can use this formula right here because we've set this up like that. And we can say, okay, the cosine of A take away negative B will be the cosine of A times the cosine of negative B plus the sine of A times the sine of negative B. Something like that. And the next step is to think about what does the cosine of negative b look like and what does the sine of negative b look like? And again, we need to think just a little bit about the Cartesian plane. So if you have an angle B, okay, maybe it's right there, then you could also have the angle negative B, which would be down here. And we can start thinking about sine and cosine. So sine, sorry about that, sine, of course, is, okay, sorry about that. So sine, of course, of B is y over r, where sine of negative b is negative y over r because you're down here in quadrant 4. So that tells us that sine b is equal to the negative of the sine of negative b. And we can look at cosine as well, but of course with cosine, as you move from angle B to negative B, cosine is x over r, so cosine doesn't change. So the cosine of B is actually equal to the cosine of negative B. So using the idea that the cosine of negative B equals the cosine of B, we can then replace this with cosA cosB. We replace sine negative B with negative sine B. And we get the simplified equation that we're looking for. CosA cosB, take away sine A sine B. And that finishes our second proof. For our fifth question, today we'll look at proving the addition identity for sine, now that we've done both of them for cosine. And the difference identity for sine, I'm going to leave that one up to you. You should be able to figure that one out on your own afterwards. So let's get started with this one. So to start this proof, we're actually going to use the cosine identities that we proved already, because there's a relationship between sine and cosine. And we're going to start by exploring that relationship. It has to do with complementary angles. So I'm just going to draw a little right-angled triangle and show you what I mean. So in this right-angled triangle, suppose we call this angle theta. Okay. Since this is a right angle here, we know that the angles in a right triangle add to 180 degrees. Well, that's 90 degrees here. So these two angles must add to 90, which is of course pi over 2. So that actually makes this angle here pi over 2 take away theta, okay, in radians. So those angles are what we call complementary angles. They add to 90 degrees. I'm going to call this side y, I'll call this r, and this x. Notice that the sine of theta is equal to y over r. The cosine of theta is equal to x over r. But if I start talking about the cosine of pi over 2 minus theta, that is also equal to y over r, because now if I move from theta to pi over 2 minus theta, this becomes the adjacent side. So what I have here is that sine theta is y over r, and cos pi over 2 minus theta is also equal to y over r. So we have what's called the complementary identity. This is true right here. You might have noticed that doing trigonometry already, that when you switch angles, the opposite and adjacent sides swap places, and so the sine and the cosine end up being equal. In fact, that's where the word co comes from in cosine, has to do with the complementary angles. You can also show pretty easily that the sine of pi over 2 minus theta is the same as the cosine of theta. So these two identities are going to be helpful. Can you see why? Well, looking back at the identity that we're trying to prove, I can take the sine of A plus B, and I can say that that is the same as finding the cosine of pi over 2 take away A plus B, which I can simplify to the cosine of pi over 2 take away A, take away B. What do I do next? Well, now that I've taken sine A plus B and replaced it with a cosine, I can use the difference identity that I put right there for you. I've already proved that, so now I can use it. Now, it's a little bit confusing how this works, but I'm going to this is the cosine of A minus B, okay, right here. And what I'm going to do is I'm going to have my A be pi over 2 minus A, and my B just be the B that's here. So I apply that formula and I write it out, and this is what I get. I get cosine of pi over 2 minus A times the cosine of B plus sine, sorry, 1 second here, plus the sine of pi over 2 minus A and the sine of B, just like that. Now notice that those identities that I just showed you up above, I can use them again here. The cosine of pi over 2 minus A is actually equal to the sine of A from this identity right here. So this is the sine of A, cosine of B, and again, the sine of pi over 2 minus A is the same as the cosine of A. And there we go. There it is. There we've proven the identity that we wanted to prove right here. I'm just going to go over one little part, because the most complicated part about this proof is the fact that when we go from this line to this line, our A value here is pi over 2 minus A, and our B value is, hang on 1 second here, sorry about that. Try that again. So the A value is the pi over 2 minus A, and the B value is just the B in this equation right here. So we're choosing to have the A be pi over 2 minus A and the B to be B, as opposed to having A be pi over 2 and then B be, like, it have to be A plus B or something like that. So it is important that in this line that we choose to expand the negative sign here and then break it up like that in order to get the result that we want at the end. So with that, we've proven 3 of the 4 identities, and the 4th one, the sine of A minus B, is going to be left for you to do as a homework question. And I think you should be able to figure out if you look at these 3 carefully. Now let's move on and start talking about tangent. So do sum and difference identities exist for tangent? Well, the short answer is yes, they do. Let's take a look. So to talk about let's start with the tan of A plus B. We could realize that that really is the sine of A plus B divided by the cosine of A plus B, because you can always do that with tangent. We can then turn around and use the sum identities that we already discovered for sine and cosine, and we would get sine A cos B plus cosA sine B, all divided by cosA cos B, take away sine A sine B. Now, you could stop there, I suppose, and say that there's your identity, but that doesn't quite feel right. Feels like a tan sum identity should involve only tangents. There is a way to do that. Here's the trick. We're going to take this fraction and we're going to divide the top and bottom of the fraction by cos A cos B. Of course, if we do that to the top of the fraction, we must do that to the bottom of the fraction. Let's take a look and see what happens when we do that. As I take the numerator of this expression and divide it by cos A cos B, I'm going to have to divide both terms by cos A cos B. So what ends up happening is I end up taking sine A dividing by cos A, but the cos B's will divide out, and I get sine A over cos A. For the second term, the cos A's cancel out or divide out, and I get sine B divided by cos B. That's just the top of the fraction. As I do the bottom of the fraction, I'm going to take cos A cos B and divide by cos A cos B. So that's actually just going to give me 1. Sine A sine B divided by cos A cos B. Nothing divides out, so I get sine A sine B divided by cos A cos B. Take a look at this expression. You should recognize a few things. Sine A over cos A is tan A. And sine B over cos B is tan B. And then in the denominator of the fraction, sine A over cos A is tan A, and sine B over cos B is tan B. So I do have this sum identity for tan. It's nice and simple there. Tan of A plus B is tan A plus tan B, all divided by 1 minus tan A tan B. There is a formula as well for the difference of tan A minus B, but again, I'm going to have you figure that one out as well on your own. And let's look at one example of how we can use this identity we just found. We'll do that for our last question today. So in this case, we're going to look for an exact value for the tan of 7 pi over 12, and I've included up there for you, you can see the tan identity that we just found. So let's get started on this one. We're going to start with the idea that finding the tan of 7 pi over 12 is really the same as finding the tan of 4 pi over 12 plus 3 pi over 12, or the tan of pi over 3 plus pi over 4. Okay, using the identity that we just got up here, that's the tan of pi over 3 plus the tan of pi over 4, all divided by 1, take away the tan of pi over 3 times the tan of pi over 4. Those are all values that we can find from our special triangles that we know. The tan of pi over 3 is the square root of 3. The tan of pi over 4 is 1. And that just gives us this right here. Root 3 plus 1 divided by 1 minus root 3. Maybe you like the way it looks if you were to write that as 1 plus root 3 divided by 1 minus root 3. And that's a pretty good answer. Now, I am going to add one other thing to this example. And that is the idea that this is technically has a denominator that's not a rational number. And you probably have never seen an example like this where you rationalize something. Like if this were just a root 3 here, then you could multiply by root 3 to rationalize the denominator, but it's 1 subtract root 3. So how do you rationalize that? Is you multiply by what's called the conjugate. Instead of 1 minus root 3, I can multiply by 1 plus root 3. Now, of course, sorry about that. If I do that, I have to do that. I have to do that on the top as well. So let's just see what happens when we do that. Using FOIL, look what happens in the denominator. 1 times 1 gives you 1. You then multiply 1 by root 3 to get root 3. And then you multiply negative root 3 by 1 to get a negative root 3. And so notice that those radicals will cancel out. And then root 3 times root 3 is just 3, or in this case, negative 3. So I'm actually going to get 1 minus 3, which is just negative 2 in the denominator. If I go back up and look at the numerator, 1 times 1 is 1. I get a plus root 3, another plus root 3, and then of course root 3 times root 3 is 3. So in the denominator I get 4, okay, and a root 3 plus a root 3 is 2 root 3. Final step in this one, I don't like the negative sign down here, plus everything is divisible by 2, so I get negative 2 take away root 3 for a final answer. Not only is the denominator a rational number, it actually in this case is 1, so it's gone. I mean, the main goal, we're looking at trigonometry in this unit, so like the main goal is getting to this step right here, okay, the 1 plus 3 root 3 divided by 1 minus root 3, and then sort of the really good solution at the end is simplifying that. There it is, simplified as negative 2 subtract root 3. Okay, thanks for your attention during this lesson, and please try the practice questions. I'm here to help you if you need help with any of those.